Explainability Assistant is a conversational agent that helps professionals to explore and interpret their data and machine learning predictions. This short video will briefly introduce the architecture of the software solution and demonstrate the capabilities of the assistant in a real-world use case. Let's get started with a short introduction. Machine learning models are algorithms that learn patterns from data to make predictions or classifications. By analyzing past data and identifying relationships, they apply this knowledge to new, unseen data. For example, machine learning models can predict energy consumption, traffic density, or even assist in medical diagnoses. While machine learning models can provide highly accurate predictions, many complex models, like deep learning, are considered black boxes because they don't easily explain how they arrive at their decisions. This lack of transparency makes it difficult to understand or trust the reasoning behind predictions, which is a significant issue in areas like healthcare, where decisions impact people's lives. To ensure AI is both ethical and reliable, it must be explainable, allowing users to understand and trust the decision-making process. This transparency not only helps build trust, but also ensures fairness, accountability, and the ability to spot biases or errors in predictions. The mission of the Explainability Assistant is to bridge the gap in explainable AI by providing professionals with a conversational interface that simplifies the interpretation of data and machine learning predictions. By making AI transparent, accessible, and private, the assistant ensures that user data is handled securely while empowering users across various fields to understand, trust, and make informed decisions based on complex models. Next, we will explore the system architecture of the Explainability Assistant and how its components integrate to support explainable AI. The user interacts with the system through chat messages, which are processed by the front end of the application. This front end functions as the conversational interface, allowing users to engage in open-ended discussions with the Explainability Assistant. As the presentation layer, the front end is designed to be flexible and customizable, offering features such as session management, user account management, and storing conversation history. Additionally, users have the ability to select which large language model is used for processing their requests, enabling them to switch models mid-conversation and cross-test results for better comparison. The front end communicates with the back end of the application through a standard REST API interface. This allows to integrate multiple front ends and existing user interfaces. The back end integrates with both user-provided data and the machine learning model, enabling predictions for new instances. This setup allows users to evaluate the model with test datasets or review predictions and their corresponding explanations. The backend constructs an LLM prompt based on user input, incorporating additional context such as available functions and conversation history. It is also capable of executing function calls to generate predefined, deterministic answers to user queries. Backend functions and their executions are a crucial component of the system. They enable the execution of various predefined routines on the data and model, providing deterministic results and ensuring consistency in the assistant's responses, which helps to avoid LLM hallucinations. Function specifications are described in JSON format, making them interpretable by the LLM, while the actual function definitions are implemented within the backend Python application. The backend makes requests to the specific large language model selected by the user through the interface. This connection is established via a Python library API with a supported LLM provider, such as Google Gen AI or Hugging Face Hub. The LLM's role is to interpret the original user query, provided as a chat message, and determine whether an answer can be generated through a combination of available function calls. These function calls, along with their parameters, are then sent back to the backend for execution. Additionally, the LLM can provide a limited free-form answer, explaining its reasoning for selecting particular function calls or clarifying why no calls could be made. Upon receiving the LLM response, the backend executes any function calls, if applicable, composes the final answer to the user query in a standardized JSON API response, and returns it to the front end, where it is presented as the assistant's response. The advantages of this architecture include the privacy of user data and models, as they never need to be uploaded to a third-party LLM provider. Additionally, the conversation remains transparent and trustworthy, with the assistant explaining its reasoning through the LLM response while providing deterministic information generated by predefined functions. Now, let's see the system in action through a brief example scenario. In the top part of the chat interface, there is a toolbar with buttons that allow users to switch the active LLM, reset the conversation history, log out to terminate the current session, and access an examples section with pre-programmed prompts. Clicking on these examples triggers the assistant's response as usual, but without the need for typing. The result is a free-form response. Let's use the Examples panel to ask the assistant about the dataset. This response consists of two parts. First, the assistant explains the process for obtaining the result and lists the function calls that will be used. The second part is a predefined template response, which is dynamically populated by executing the corresponding function in the backend. Notice that in this case, the template response ends with a question. Since the assistant is aware of the conversation context, a simple yes from the user is enough for it to understand that more in-depth statistics are being requested. This time, the template response is populated with a table displaying the computed dataset feature statistics. Let's say we want to study some outliers. We can ask the assistant how many data samples have an outdoor temperature warmer than 28 degrees. Notice that we are using the word warmer, and the assistant correctly interprets this common knowledge and translates it into a function call with the appropriate parameter to filter the data by the minimum value of the outdoor temperature feature. We can use another contextual question to take a closer look at this group. Now, let's close the Examples panel and see if we can learn more about the model currently loaded into the backend. This predefined template answer provides a general description of the genetic programming model that is ready to use, and even includes the exact program dynamically extracted from the model file. Let's say we want to dive deeper into a particular data sample. Users can make complex queries that may involve multiple function calls. In this case, the results of these calls will be combined into a single message, but the output remains structured and populated from predefined templates. The Explainability Assistant helps users understand how different features contribute to the final prediction by using a SHAP explainer. Feature importances are computed dynamically in the backend. Additionally, the assistant can provide more detailed information about the methods it uses, offering transparency into the underlying processes. Meanwhile, we switch to a llama model in the middle of the conversation, while preserving the context. Another way to explore the effects of different data features on the prediction is by asking what-if questions. In this case, the LLM infers the context for a function call, and the backend substitutes the specified value, handles the necessary calculations, and returns the result within a dynamic template. We can take our exploration even further by leveraging counterfactual explanations, generated dynamically in the backend using the DICE module. Counterfactuals allow us to explore hypothetical scenarios, showing how different values would lead to different model predictions, and helping to deepen our understanding of the model's behavior. Finally, we can ask the assistant to use the model to predict a new data sample by providing updated feature values. This concludes our brief overview of the application in the energy consumption use case. The Explainability Assistant is available beyond this scenario. It offers even more functionality and is easily adaptable and extendable to support a wide range of datasets, models, and business use cases. With its flexibility and transparency, it can be a powerful tool for professionals across industries, helping them make informed, data-driven decisions.
We hope you have enjoyed this presentation.